Hey everyone, this is Hanson. One more time. At the start of that lesson 4 of chapter 9, I had mentioned that that was going to be my last video, and now here I am making one more. So I'm just kind of laughing at myself, thinking I'm going to make them shorter and wrap up with buffers. So welcome to your last video lesson in chapter 9, I promise. So let's talk about buffers. You ever take a buffered aspirin or hear about buffered solutions? A buffer is a solution whose pH changes very little when an acid or base is added. So it resists a change of pH. Most buffers are solutions that are composed roughly in equal amounts of a weak acid and its conjugate base. A weak acid and its conjugate base, and typically the conjugate base will come from the salt that has the same last name. So let's say, for example, acetic acid. This is vinegar, HC2H3O2. Sometimes you see it written in the organic chemistry style, carboxylic acid. Hydrogen acetate, or carboxylic acid style, CH3COOH. Both of those are exactly the same formula. It's for acetic acid. And that's an example of a weak acid. And a salt that shares the same last name could be sodium acetate, NaC2H3O2. Acetic acid is a weak acid, and sodium acetate would have its conjugate base A negative. So a buffered solution resists the change in pH because if I add strong base to the solution, there's an acid in there that reacts to neutralize it. The weak acid will react. I'm trying to make my page stop moving. And the H3O plus that could be added reacts with the conjugate base. So a buffered solution really is a team of chemicals that react with either an acid or a base to neutralize it. So if I have a team of chemicals, one of them being an acid, the other being a base, I'm all equipped to neutralize either an acid or a base to help a resistance of change in pH. Now let's take a look at this diagram to get a sense of what's going on. Do you notice that in pure water, we have a pH probe sitting in a jar of water here, and a pH is reading 7.0, which represents exactly a neutral solution. When I add a strong base, NaOH, to the solution, as the arrow is taking me here, notice how basic it becomes very quickly. It goes to 12.3 pH units very quickly. And if I were to add a strong acid to the beaker of water here, the solution becomes quite acidic very quickly. And that makes sense. When you add an acid to water, it should become acidic. When I add a base to water, it should become basic. But now instead of pure water, what if inside this beaker we had a buffered solution? And remember the buffer? It's a weak acid and its conjugate base. Those are a team of chemicals. You have a weak acid with its conjugate base. In both of that solution, there's a team of chemicals there. So now let's add the same quantity of acid to this. Remember, it's up here, 0.02 molar HCl, and the pH changed drastically to 1.7. But now what is it at? In a buffered solution, it still changed, but not as drastically. It only dropped to 4.7, which is less acidic than what it was up here at 1.7. Doing the same idea here with the 0.02 molar NaOH, see how it went to 12.3 in the unbuffered solution? And now it's at, it says 4.77, but that really should say slightly basic. But so our solution went up a little bit from 4.74 to 4.7 It went down a little bit. It's a little bit of a swing to be a little acidic. And from 4.74, just a little bit higher, went a strong base. So it resisted a change of pH. When a strong acid or base was added, it changed just a little bit. Buffers help solutions resist changes to pH even when you pour in strong acid or strong base. Now, to be a buffer, you need to have a weak acid and their conjugate base. Let's write out the Bronsted-Lowry acid-base reaction between acetic acid, and I'm going to write it this way, HC2H3O2. That's the acetate ion. And I'm going to react that in just a Bronsted-Lowry proton transfer, where acetic acid donates a proton, forming its conjugate base, acetate, and the conjugate acid of water is hydronium. Write out the Ka expression, which takes us the products over reactants, where the water will drop out. So we have the conjugate base, H, was donated to the water, right? This hydrogen was donated to the water, so that gives us the conjugate base of acetate, times the conjugate acid of water, which is hydronium, all set over the original molecule of acetic acid. So here we have just products over reactants, giving us the equilibrium constant known as Ka for acids. What if we were to rearrange this for the hydronium ion concentration? So let's isolate this variable. Well, the first thing I would do is to multiply both sides. Let me just rewrite. Ka is equal to the acetate times hydronium all over the molecule. Whoops. Let's multiply both sides by the molecule, HC2H3O2. And when we do that, we can see that this would cancel, and we'd have over here Ka times the acetic acid, and now we've dropped out. So then what? We want to isolate H3O+. So now I'm going to divide both sides by the conjugate base acetate so that they'll cancel out. And we've isolated H3O+ to be on a side all by itself, right? And here's what we did. We have HC2H3O2 times Ka over C2H3O2 negative. The acid over the conjugate base. And really what you'll see this presented as is the Ka will be placed outside. So if I really wanted to clean this up, I would take the acid formula, set over its conjugate base, and you'll see Ka written outside, and then you'll see that set equal to H3O+. All right, so we've just rearranged the Ka expression to isolate hydronium. All righty, well now what? If we take the negative log of both sides, we get something called a P, right? A pH, a pKa. And let's show what that looks like. When we take the negative log of both sides, we find that rearranging just to represent the conjugate acid and the conjugate base over each other in this ratio. Here was our hydronium. Here's the Ka. right? So if this ratio doesn't change much, the acid and the base concentrations, you can see how the pH, which is this guy here, right? If I can hold this concentration relatively constant, we're going to see that the pH remains constant. Well, let's practice. Let's determine whether a solution containing each of the following substances is a buffer. Explain your reasoning. Now, let me just remind you the criteria. Buffers must be a weak acid with its conjugate base. So let's say HBr and NaBr. Right away, I can see that this is a strong acid. That doesn't meet the criteria, does it? Since HBr is a strong acid, that's not going to be a buffer. No. How about 2? HF and KF. This is a weak acid, so that meets the criteria. And F negative is the conjugate base of HF. So the negative ion is correct. So yes, this would be a perfect buffer. Choking. How about letter C, or number 3? CH3COOH. This is acetic acid. Sometimes you see it written in the inorganic hydrogen acetate or the organic just 2 different divisions of chemistry. Inorganic, we would call this hydrogen acetate or acetic acid. In organic chemistry, we write that as Cu, with this being the ionizing proton, just recognizing it either direction. Notice it says alone. Well, no, because you need to have the conjugate base with the acid. So no, that's not going to be a buffer. It's a good acid, but we need its conjugate base in the solution as well. So the only one that would work in this criteria is the second example, a weak acid with its conjugate base. Consider a buffered solution prepared from the weak acid, bicarbonate, and its conjugate base, carbonate. So here is the acid. Here is its conjugate base. So this is in a buffered solution. Explain why both HCO3 negative, this is what we call bicarbonate, and a carbonate, CO3 minus 2, are needed to prepare the buffer. Well, think about Le Chatelier. If I increase the concentration of one, we're going to shift this direction. If I increase the concentration, we're going to shift the direction. We need something on both sides of the arrow so that when a stress is added, we're able to combat the stress. So we need both the acid and the base to be sure we can counteract any stress. Let me just make that even more clear. We need an acid and a base, and it's called its conjugate base. We'll need what? Because what if we added base? The acid would be there to neutralize. And what if the stress that we added was adding an acid? Well, we'd have a base ready to counteract that stress. So you need both in order to have the ability to neutralize. The addition of a base is neutralized by the acid. If we added an acid, it will be neutralized by the base. Either stress has something ready in action to help resist the change in pH by Le Chatelier's principle. I'm trying to erase that there. What happens to the concentrations of bicarbonate and carbonate when a small amount of acid is added to the buffer? What happens to the acid? If we add acid, What does it react with? It reacts with the base. So what would happen? Well, the concentration of carbonate, CO3 minus 2, would decrease because it's being used to neutralize the stress of adding an acid. Think about Le Chatelier. If this is the stress, I'm adding acid, and that's the definition of an acid, right? Adding acid, it's going to cause the equilibrium to shift to the left. And when it does so, the concentration of the carbonate, CO3 minus 2, goes down. And the concentration of bicarbonate actually increases because you're pointing at it. You're going to make more of it as you point to the left. So when I add acid, I use up base. This concentration went down as this concentration went up. That was number 2. How about 3? What happens to the concentrations of bicarbonate and carbonate when a small amount of base is added to the buffer? Well, what does the base do? If this is the stress, you're adding base, it's going to react with the acid in the equilibrium. Right? So let's clean this back up and just talk through what happens here. If I add a base, it's going to react with the acid, isn't it? So here we labeled, this is the acid, this is its conjugate base. What happens, we said, when we add base, it's going to react with the acid. So the acid gets consumed. You want to make more, right? So think about what Le Chatelier would say. This now is the acid, right? This is the acid ion. And when you add base, it's going to consume the acid. That goes down. That means you're going to shift to the right to make more. The bicarbonate is the acid. Its concentration gets lowered because it's being consumed to neutralize the base that was added as the stress. And because we're shifting to the right, the carbonate actually increases in concentration because you're making more, you're pointing at it. When you add base, you use up the acid. So this is the stress. That means we'll shift to the right. The opposite of lowering the hydronium is to increase the hydronium. So you point at it. So when I think about the stress, let's go back and just kind of emphasize Le Chatelier's principle. It's really playing a role here. This is the acid ion, right? It's what we measure pH with, isn't it? Hydronium. If you add acid, such as in this example, you add acid, that's your stress. It's going to shift the equilibrium this way. If you add base, the stress is consuming that, and it's going to shift the equilibrium this way. So really, a buffered solution is just an application of Le Chatelier's principle. The acid dissociation constant, Ka, we rearranged that, remember, a moment ago, to solve for the pH. Let's rearrange this and solve for the determination of a pH of a buffered solution, right? What is the pH of a buffer that contains 0.2 molar acid and 0.2 molar conjugate base? The Ka is given to us as 1.8 times 10 to the negative fifth. I can find the concentration of hydronium by taking the Ka and multiplying it by the concentration of the acid whoops, they wrote it in organic style, acetic acid, CH3COOH, cool. And we set that over the concentration of the base, which was, from the salt here, also 0.2 molar. Remember, the salt, sodium is just simply a spectator, and the conjugate base down there would be acetate. Do you see how those two numbers really just fall apart? So they cancel one another. And so if hydronium is equal to 1.8 times 10 to the negative fifth, I can find the pH very easily by taking the negative log of the Ka. When a buffer is an equal concentration with its conjugate base, the acid and the base are of equal concentration, that ratio just falls out. pH can be found by taking negative log of the Ka. Let me hit that. Whoops, clear screen. Negative log of 1.8 E negative 5. My screen reads 4.74 pH units. Cool. Let's calculate the pH of the dihydrogen phosphate buffer. Given the following concentrations, here's our Ka value. So the hydronium ion concentration is equal to the Ka times the concentration of the acid over base. The dihydrogen phosphate contains more hydrogen, right? So that's H2PO4 over HPO4 minus 2. Alrighty, so here we have in letter A what we call the ideal buffered solution. They are of equal concentration, aren't they? So in Ka, 6.2 times 10 to the negative 8th times the concentration of the acid, which is 0.1 molar, over the concentration of the base, which is also 0.1 molar, which means this just falls out, doesn't it? So if this is the hydronium ion concentration, pH would be negative log of the Ka. I'll hit that for you. Negative log of 6.2 E negative 8. I got 7.2, and I'll just round, 7.21 pH units. Now, do you notice in letter B, we have 1 molar and 1 molar? It's going to cancel out. pH is going to be the exact same number. Letter C, we have a 0.5 and a 0.5. They're going to cancel out, so we have the exact same number. The pH is equal to the negative log of the Ka whenever the ratio of acid to base is the same number. Right? I can put 0.1 over 0.1, that cancels. I can put 1 over 1, that canceled. 0.5 over 0.5, that canceled. And pH was found by taking the negative log of the Ka value each time to find the exact same number. And that, my friends, ended the lessons. The end. I'm so proud of you. You've got whoops, I can spell too. You're so proud of you. There we go. Go ahead and finish up your notes, submit them into your Dropbox, begin your homework. You've made it. Congratulations.